air masses, mid-latitude cyclones, and weather, this information pertains to really to chapters 19 from your textbook, but we're tying it to also to exercises in your lab book, and I'll be running through some examples showing you how to plot weather data, how to interpret weather fronts. But first, I want to go ahead and do the first part of this, which is going to be to sort of review and give an overview of air masses and the kinds of fronts, and then we'll go on to talk about winds, data, and then how we kind of identify fronts from a map. All right, so air masses, air mass properties, and fronts come into play first. What should we be able to do here? Well, the overall concept here is to kind of connect the image on the left, which is what we call a mid-latitude cyclone, and the image on the right, which is a cartoon showing the different kinds of air masses that we have. The distribution of air masses around the Earth's surface is a function of moisture, which is connected to the distribution of the continents, but it is also a function of temperature. And what we find here in the mid-latitudes, where the U.S. is, but also in the southern hemisphere, is a boundary between essentially what are warm or hot air masses on the bottom and cold air masses, okay, on the top. And it's the intersection or the convergence of these air masses as they come together which ends up creating fronts, coupled with atmospheric circulation and the Coriolis effect, and we end up with a fairly complex, it looks a little bit like a quotation, set of interactions and a weather distribution that moves, in this case, from west to east, okay, with the westerly winds across the U.S. On the right-hand side, as I said, it's cold on top and warm on bottom. And then east to west, we have some additional boundaries here. Okay? Air masses such as the maritime polar air mass or the maritime tropical air mass, these are over an ocean, so they tend to be wet. Okay? Maritime polar and maritime tropical on the east coast or coming out of the Caribbean are also going to be wet. Okay? And then we have three air masses here in the center of the diagram that are dry. Continental tropical air mass, this really forms in the summertime when the continental crust is able to heat up. And then we have Arctic, okay, and polar air masses, which tend to push down to the south. The air masses, the relative amount of moisture, top to bottom, as a function of the saturation mixing ratio you should be familiar with, is that they are wet on the top, right, and wet over the oceans and wet over the other oceans, but if in the Pacific and the Atlantic. But we also should point out that cold air masses, or just remind ourselves that cold air masses hold less moisture than warm air masses do. Okay. When these things come together, they tend to create a kind of boundary. So the air masses, because they contain different amounts of moisture and have different temperatures, they're going to have different densities. This produces relationships that in which air masses will not mix. Okay? There may be some mixing along the front itself, right in this area here. Actually, I'll go ahead and erase that for right now. You could have some mixing, but more or less they stay as separate bodies. And what happens if we're talking about air masses that move from left to right in this diagram, so we're going to call this west to east. If we have a cold air mass, which is dense and heavy, which catches up to and moves into the back of a warm air mass, which I show on the right-hand side here, what's going to happen is it's going to plow underneath and it's going to create a steep boundary, okay, pushing air in the warm air mass up. This typically results in unstable conditions or unstable air mass or airflow conditions. It produces cumulonimbus clouds, thunderstorms, heavy rain, and those kinds of activities. That's called a cold front. If we take a look at another kind of front, okay, a warm front. Now, you're probably familiar with this already from looking at the news, or watching the news, I should say. You have a warm air mass that catches up to the cold air mass, right? So both air masses are kind of moving in the same direction, but one is moving more quickly than the other. As the warm air mass rides up over the cold air mass, because it is less dense, the boundary, though, I'm going to change colors one more time here. The boundary shown here is not as steep. Okay? And so the fact that it's not as steep means that the air is going to rise more slowly, okay? And you're going to have stable lapse rate conditions, right? So where the air temperature has time to cool off as it expands, and it ends up being colder than the surrounding or the environmental rate. And so you don't get thunderstorms. What you do get is wide zones of precipitation. You get nimbostratus, so those are layered clouds producing rain, as well as a variety of alto and cirrostratus, and then even at the highest altitudes we'll get ice-bearing clouds such as cirrus clouds. Okay? Note the symbol down here on the bottom, and I'll step back one slide to show you the cold front symbol. It's half circles that are on the side in the direction of movement. So movement here is from west to east or left to right, depending on, I'm thinking about looking kind of at the U.S. map, sort of north at the top of my page, so west to east. And so movement here is from west to east with the half circles in red pointing in the direction of movement. If I just back up here for a second, it's a little bit of a mess, but we'll just kind of clean it up. Okay? Notice the symbols for the cold front. Okay? Those symbols for the cold front here in blue are teeth, okay? Just like they are for a thrust fault. Also, again, the teeth are pointing in the direction from west to east or from left to right, in the direction that the front is moving and that both air masses are moving. The last type of front is a little bit ambiguous for some people when you look at it on the weather map. It's called an occluded front. And the occluded front is actually the joining. So down here on the bottom, I'm going to make a little dot, and I'm going to draw a line right here. Okay? The occluded front is actually the joining of two different fronts. The cold front and the warm front are going to collide. The cold front moves a little bit faster than the warm front from west to east. It catches up to the warm front and they intersect, right? Well, what does that do? It has the effect of doing this. It creates a lot of weather over a wide area. It produces weather over the cold front and the same weather that's associated with the warm front. They kind of are collapsed onto or next, sorry, not onto, but juxtaposed next to each other, which creates a wide zone where you can get thunderstorms, snow, long-term heavy precipitation, all of those things. And what is happening here is that the cold air on the left, cold air here, and cold air on the right have come together and have lifted up the warm air mass. So unlike a cold front or a warm front where you're really dealing with two air masses, now we have all three, not all three, but three different air masses which have come together to produce this occluded front. I've gone ahead and drawn the symbol down here, and I'm just going to shade it in green for you. Okay, you'll notice it's a mixture of the two basic symbol types, triangles or teeth, and then the half circles, and they're again on the side of in the pointing in the direction in which the front is moving. Okay? So when all of these air masses come together, you produce a cloud distribution that you see on the left-hand side here, and you'll notice there's an area in here. I'm going to try a different color. Maybe we'll just go with straight black for this. Try a different color on the left-hand side, where you see this area in here that I'm shading in has no clouds in it. Okay? That area is the cold air mass. Okay? So on the right-hand side of the diagram here, the cold air mass down at the bottom here is shown in this side view of the air masses. So we're looking along, let's say, line E to line A, or sorry, to point E to point A along that line. So this is cold in here, cold, okay, right here. And then we have a pretty sharp boundary right here where I can put the teeth on this. That's your cold front. So that means I've got to have a warm front on the inside of this, warm in here. And then, of course, we got to have this guy, which is our warm front. Okay. Remember, the warm front sits underneath all of the clouds. So in the schematic here, the cartoon on the right, you can see that the front is here. Okay. The warm front, and the warm front sits right beneath all of those clouds. So it's a wide zone. Okay? And then on the last area, which is out here, okay, all of this should be cold as well. That would be an example of that would be your maritime polar. Okay? What kind of air mass would be pushing up from below here? Well, this would be your tropical air mass, right? Your maritime tropical. And then what's the cold air that's kind of pushing in like this, where we have cold, heavy air? We're talking about something like a continental polar. Okay, so that's a connection and just an overview of the different air masses, how the different fronts, and how air masses come together and make fronts, and essentially develop this kind of low pressure system that we've talked about in lecture. Here, it's all centered on this low pressure system, as well as multiple fronts. Now, what's not shown on here, I'll draw in here is, just briefly before I wrap up, is the occluded front. And the occluded front's going to come off of the tips of the joint here, where these two fronts are joined together. The occluded front, it's kind of like a zipper. Okay, the occluded front is here. I'm just drawing it in right on top of the low pressure system, and eventually what's going to happen is the cold air front, or the cold front, is going to migrate up, and it's going to close this distance on the right hand side, and it's going to shut down the system. And it shuts down the system by doing this, by lifting the air that's warm and sending it aloft. Okay? Once we have a stratification, a vertical stratification, the system's going to shut down. So we don't have any more vertical movement of air. That's what's driving the system, right? Cold air is sinking and warm air is rising. It's that kind of vertical movement which creates low pressure and high pressure systems, and that's what drives wind and the horizontal motion of air masses across the ground. So now once we've lifted that stuff up and created a kind of warm air on top, cold air on bottom stratification, the system runs out of gas. Okay? So we'll talk about how this is related to hurricanes in some ways, and that will maybe make a little bit more sense in the future. Okay? So next up, we'll talk a little bit about plotting weather data, and interpreting weather data, and trying to identify fronts on weather maps. And we'll also cover the concepts of pressure and wind, although we've done that in previous labs.